All right, let's dive right into a massive topic for Class 12 chemistry: solutions. Now, when you hear the word solution, you probably just picture stirring some salt into a glass of water, right? But honestly, in real life, we almost never come across truly pure substances. Think about it. The brass used to make musical instruments, that's actually a solid solution of copper and zinc. The intravenous injections they use in hospitals, those are incredibly carefully balanced solutions designed to perfectly match our blood plasma. Even the tap water you drink is a solution. Did you know that just 1 part per million of fluoride ions in water helps prevent tooth decay? But if you bump that concentration up too high, it literally becomes rat poison. That is the incredible literal life or death power of concentration. So let's jump into this explainer and master the science of mixtures. Here is our quick roadmap for today. We're going to cover an introduction to solutions, expressing concentration, solubility and gas laws, ideal versus non-ideal solutions, colligative properties, and then we'll wrap it all up with a summary and some practice questions.
Okay, Section 1, Introduction to Solutions, the basics of mixtures. Let's get into it.
So what exactly is a solution? The absolute key word here is homogeneous. That simply means the composition and properties are perfectly uniform throughout the whole thing. Picture dropping a simple sugar cube into a beaker of water. As it dissolves, the water molecules, which we call our solvent, completely surround the sugar molecules, our solute. They pull those sugar molecules apart until they're evenly, perfectly distributed. Now, the solvent is usually whatever component you have the most of, and this is crucial. It dictates the physical state of your final solution. Since water is a liquid, our sugar water becomes a liquid solution.
Now, it's super easy to just assume all solutions are liquids, but that's actually not the case at all. We have gaseous solutions. The oxygen and nitrogen mixture in the very air we're breathing right now is a gaseous solution. We also have solid solutions. Think of an amalgam of mercury with sodium or even copper dissolved in gold to make jewelry stronger. For your board exams, definitely remember that a solution can exist in any of the 3 states of matter. It entirely depends on the solvents. Moving right along to Section 2, Expressing Concentration, the essential math. Okay, there are 7 essential ways we can express concentration, and you'll need to know all of them. But here is a massive exam tip for you right now, so listen closely. Pay special attention to molarity versus molality and mole fraction. Molarity, spelled with an R, measures the moles of solute per liter of solution. Because it relies on volume, and we know liquids expand when they're heated, molarity actually changes with temperature. But things like mass percentage, parts per million, mole fraction, and molality are based entirely on mass. Mass doesn't care about heat. It doesn't change. Therefore, those are completely independent of temperature. Examiners absolutely love testing that specific distinction. Let's actually walk through a classic calculation together, finding the mole fraction. Imagine we've got a 20% by mass solution of ethylene glycol, which you'd commonly use as car antifreeze. Step 1, just assume you have a 100-gram sample total. That instantly gives us 20 grams of glycol and 80 grams of water. Step 2, convert those masses straight to moles by dividing by their molar masses. That leaves us with 0.322 moles of glycol and 4.444 moles of water. Step 3, to find the mole fraction, simply divide the moles of our target component by the total moles. So 0.322 divided by the total, 4.766, gives us 0.068. See? It's simple, logical, and guaranteed to earn you full marks. Section 3, Solubility and Gas Laws, the Rules of Nature.
Have you ever wondered why salt dissolves so easily in water, but completely fails to dissolve in benzene? Well, the golden rule of solubility is like dissolves like. Polar solutes dissolve in polar solvents, and nonpolar dissolves in nonpolar. But what exactly happens over time as you mix them? At 0 seconds, you add your solute, and dissolution begins. But as the concentration creeps up, those solute particles start colliding and separating out again, a process we call crystallization. Eventually, you hit this fascinating state of dynamic equilibrium. This is where dissolution and crystallization are happening at the exact same rate. Once you hit that perfect point, your solution is officially saturated. It literally cannot hold another drop of solute.
So what about gases dissolving in liquids? That brings us right to Henry's law. It states a very simple rule. Gas solubility in a liquid is directly proportional to its partial pressure. Think about a standard bottle of soda. Why is it packed under such high pressure at the factory? Because, according to Henry's law, forcing it under high pressure forces the carbon dioxide gas to dissolve right into the liquid. The very second you twist off that cap, the pressure drops, the solubility drops, and all that trapped gas aggressively escapes as fizzy bubbles.
But what happens if we mix two volatile liquids together? Enter the brilliant French chemist Francois-Marc Raoult. Back in 1886, he formulated what we now call Raoult's law. It dictates that in a solution of volatile liquids, the partial vapor pressure of each component is directly proportional to its mole fraction in the mixture. It is this beautifully elegant equation that links the actual physical pressure of vapor escaping a liquid directly to the mathematical fraction of molecules present. You really want to lock this down, because this law is the absolute foundation for the rest of this chapter.
Section 4. Ideal versus non-ideal solutions when solutions rebel.
When we look at how an ideal solution behaves mathematically, we can plot mole fraction on the x-axis against vapor pressure on the y-axis. In a perfectly ideal setup, the partial pressures of the individual components form perfectly straight linear projections, and the total vapor pressure perfectly follows along too. What this means on a molecular level is that the interactions between the completely different molecules in the mix are identical to the interactions they had when they were just in their pure states. Everything is perfectly balanced. But, as we know, the real world doesn't always play perfectly by the rules. Most real-world mixtures form non-ideal solutions. When molecules of liquid A and liquid B interact differently with each other than they do with their own kind, they deviate from Raoult's law. If their new interaction is weaker, vapor escapes way easier. We call that a positive deviation. If the new interaction is stronger, vapor gets trapped. That's a negative deviation. Some mixtures, like a 95% ethanol and water blend, deviate so heavily they form what is known as an azeotrope. That means they end up boiling at a constant temperature and you literally can't separate them using simple fractional distillation. Section 5. Colligative Properties. Power in numbers. Here is the absolute most important thing to remember for this section. Colligative properties depend strictly on the number of solute particles present in the solution. They completely 100% ignore the identity of those particles. Whether you dissolve 1,000,000 molecules of sugar or 1,000,000 molecules of urea, the physical impact on your solvent is exactly the same. Adding a non-volatile solute physically blocks solvent molecules from escaping, which causes a relative lowering of vapor pressure. This kicks off a chain reaction. Now you have to heat the solution more to boil it, that's elevation of boiling point, and you have to cool it down more to freeze it, depression of freezing point. This property is exactly why we pour antifreeze into our car radiators. The fourth and final colligative property is osmotic pressure. Now, osmosis itself is just the natural flow of a pure solvent through a semi-permeable membrane, moving into a more concentrated solution. Osmotic pressure is the exact amount of physical force you would need to apply to stop that flow dead in its tracks. And hey, this isn't just theoretical lab science, it's literally human biology. If you drop blood cells into highly concentrated, hypertonic saline water, water rapidly rushes out of the cells through osmosis and they completely shrink. But if that water is hypotonic, meaning it's too pure, water rushes into the cells and they dangerously swell up. A perfect balance is absolutely essential. Section 6. Summary and practice questions. Capstone exam prep. You made it through the theory. Incredible job. But before we jump into the math, let's lock in your 5 essential pillars. Number 1, solutions can be any state of matter. Number 2, really know your concentration formulas inside out. Number 3, Henry's law is for gases under pressure. Number 4, Raoult's law is your baseline for volatile liquids. And number 5, colligative properties care only about the number of particles, not what those particles actually are. Have all that memorized? Fantastic. Let's practice. Let's hit a couple of rapid-fire conceptual questions straight from the textbook exercises. First up, define the term solution. We definitely know this one now. It's a homogeneous mixture of 2 or more components. Okay, now for the slightly trickier one. Give an example of a solid solution in which the solute is a gas. Remember that table we looked at earlier? The correct answer here is the solution of hydrogen gas dissolved in solid palladium. If you remembered that detail, you are absolutely thinking ahead. Okay, let's step it up with a high-yield calculation. Exercise 1.4 asks for molarity, given a 68% mass percentage and the density. Quick exam tip. Whenever you see density in a question, remember it's your mathematical bridge between mass and volume. Assume you have 100 grams of solution. That instantly means you have 68 grams of nitric acid. Use the molar mass of nitric acid to find your moles. Then, take that 100 grams of total solution and divide it by the given density, 1.504 grams per milliliter, to find you exact volume in milliliters. Convert that volume right into liters, divide your moles by your liters, and boom, you have your molarity. Next up, let's look at exercise 1.8. This one brings back our antifreeze example from earlier, but this time it asks for molality. Remember the rule? Molality is moles of solute per kilogram of solvent. First, take the 222.6 grams of ethylene glycol and divide it by its molar mass, which is 62 grams per mole, to get your moles of solute. Next, look at your solvent. You've got 200 grams of water. Convert that directly to kilograms, giving you 0.2 kilograms. Simply divide your moles by 0.2, and you have perfectly calculated the molality. Easy as that.
And finally, let's look at a classic board exam curveball. Exercise 1.9. A water sample has 15 parts per million of chloroform. To express this in percent by mass, remember that 15 ppm literally means 15 grams per 1 million grams of solution. So 15 divided by 10 to the power of 6 multiplied by 100 gives you the mass percent. Now, for the molality, use that 15 grams to find your moles of chloroform and divide it by the mass of the solvent in kilograms, which is practically the whole million grams minus the 15. Mastering these kinds of multi-step conversions is exactly what will put you in the top percentile.
You've got the tools, you've got the equations, and you totally understand the logic. Master the math, understand the laws of nature behind the formulas, and mastering your board exams honestly becomes so much easier. Use this explainer as your ultimate study guide, and go finish the rest of those textbook exercises with total confidence. Thank you so much for joining me today. Now, I want to leave you with one final question. What chemistry chapter should we demystify next? Stay curious and keep learning.